Hi everybody, welcome back to AP Chemistry, Chapter 4. Jessica said this is Lesson 7, so we're going to go with that it's Lesson 7. I can't really remember. I think it is Lesson 7. In this lesson, basically, what we're adding on is calculations with acidic and basic solutions and reactions between acidic and basic solutions. So we need to define what an acid is because it's been a while. There are different definitions of acids depending on who you talk to. There's an Arrhenius definition of an acid and a Bronsted-Lowry definition of an acid. An Arrhenius acid is defined as a substance that when you put it in water increases the amount of hydrogen ions. So there are things that dissociate either completely, like our strong acids, or slightly to increase the amount of hydrogen ions when you put them in water. A Bronsted-Lowry acid is defined as a proton donor, which really is the same thing, because if you think of the hydrogen atom, this has one proton and one electron, no neutrons, because you get neutrons by subtracting. If hydrogen has a +1 charge, if it's the hydrogen ion, then it has lost an electron. So all the hydrogen ion is, all the H plus really is a proton. So there's really no difference between an Arrhenius acid and a Bronsted-Lowry acid, except for the wording. This is a hydrogen ion donor, this is a proton donor. They are the same thing though, that's important that you know. The way that you recognize acids is that they either have H first, or they have their organic acids, which are all weak acids, and they have the Cu group at the end of their name. So that's how you can recognize an Arrhenius or a Bronsted-Lowry acid. They are really the same thing, okay? An Arrhenius base is a substance that increases the concentration of hydroxide ions in solution. So these are metals with OH. That's how you can recognize an Arrhenius base. A Bronsted-Lowry base is completely different. You do not need to have OH in you. You simply need to be able to accept a proton. So for example, these are funky bases like NH3, CH3, NH2, etc. Okay? They don't have to have OH. Of course, all these guys are still Bronsted-Lowry bases, but there are some Bronsted-Lowry bases, obviously, that don't fit the Arrhenius equation because they are not metals with OH. Okay? So acids and bases get together to neutralize each other. You can see here this is our acid because it has H first. I don't think you have this reaction in your notes, but it's okay. This is your base. It's a metal with OH. And it is simply, if you notice, just a double replacement reaction. It's another double replacement reaction. So you make calcium nitrate, which is your salt, and you make water, okay? So we say that acids neutralize bases because what you end up generating is salt and water, which are mostly neutral compounds. Salts can have acid-base properties. Again, this is just another idea of a Bronsted-Lowry acid or base. The acid is the proton donor, the base is the proton acceptor. So since water here lost the proton to NH3, water is the proton donor and serves as an acid in this reaction. Whoops. And NH3 accepts the proton and becomes NH4. It's the proton acceptor. It's the base. Okay. So I know you're dying to get to the, we call these reactions of an acid and base a neutralization reaction. I know you're dying to get to the nitty-gritty and the problems with these, so let's head to those. We'll do a couple blah, blah, blah examples. We will be performing calculations with these. Oh my. There we go. And these are the same thing as in your notes. I say, again, if you're going to mix two solutions, you have to figure out what's going to happen. So if you mix an acid with a base, the acid's going to give its proton to the base is going to accept it. Again, you'll find moles if you can, figure out who's limiting where appropriate, use the moles of the limiting reagent to find the product or whatever they ask, and then convert to the desired unit they ask. Same exact steps we've been doing in every type of problem. So, really straightforward example. What volume of 0.1 molar HCl is needed to neutralize 25 mils of 0.35 molar NaOH? So, where do you start? Is a reaction going to happen, and what is it going to be? You start with your reaction, right? That's always the first place you start, is with your reaction. We have HCl, and we are, hopefully you recognize that as your acid, and you're reacting that with NaOH, which again is a metal with OH, so hopefully you recognize that as your base. Acids and bases just undergo proton transfer. It's a double replacement reaction. So now the Na will be with the Cl, and this is +1, and this is -1, so that's fine. You don't need to crisscross. And the H is with the OH. And you can leave this written as HOH, or you could leave it written as H2O. It doesn't matter. I put my given information underneath my reaction, so I'm given 25 mils of 0.35 molar NaOH, and I've given 0.100 molar HCl. So obviously this is not a limiting reagent problem because I don't have enough information to find moles of this. In fact, they're asking me the volume of that. So what can I get with what I'm given? Well, I can find moles. I have the molarity of my base, I have the volume of my base, so I can find moles. I'll just rearrange this equation to solve for moles, which is molarity times liters. My molarity is 0.35, and my liters are 0.025. So my moles of NaOH, I'll grab my calculator here, 0.35 times 0.025, you get 0.00875 moles of the NaOH, and now I can convert that to moles of HCl by doing a mole-mole between my reactants. Oh, according to the equation, that probably works out better anyway. For every 1 mole of NaOH, I need 1 mole of HCl. So that will give me 0.00875 moles of HCl. So now if you think about what I know the molarity of HCl, and I know the moles of HCl. And if you have the molarity right here, and you have the moles, you could rearrange this to solve for volume, okay? I don't really like green. Molarity equals moles over liters. I have the molarity of HCl, 0.100. I have the moles of HCl, 0.00875. I simply am going to rearrange this equation to solve for the liters. So I slap this over 1 and cross multiply, and then divide both sides by the 0.1. And you get 0.0875 liters, which is the same as 87.5 milliliters. That is your final answer. And you don't have to put it into milliliters. I don't know, it's just, I don't like the number 0.0875, I like 87.5. Straightforward, again, same stuff. We found moles, we did a mole-mole between what's given and what's asked, and then we used the given information to solve for the desired unit. All right, in a certain experiment, 28 mils of 0.25 molar HNO3 and 53 mils of 0.32 molar KOH are mixed. Calculate the amount of water formed in the resulting reaction. What is the concentration of H plus and OH minus ions in excess after the reaction goes to completion? Probably both are not going to be in excess. Maybe. I doubt it. We'll see. So we're mixing, again, we start with the reaction. We are mixing HNO3 with KOH. The acid with the base. They undergo double replacement. You make KNO3 and H2O. Okay? We're given 28 mils of 0.25 molar HNO3, and we're given 53 mils of 0.32 molar KOH. So I'll find the moles of each of those. This should be 0.007 moles. And this will be 0.01696 moles. Okay? They want the amount of water, and they want who's in excess. Okay, so since I am given moles, or I have enough information to find moles of both my reactants, it is a limiting reagent problem. I will need to see who runs out first. Again, they have the same coefficient, so whoever there is less of will run out first, which happens to be the HNO3. This is your limiting reagent. This will be in excess. So when they want the concentration of H plus, I think it should be or OH minus in excess. We'll be finding OH minus in excess. Once I know who's limiting, I use the moles of it to find the moles of my product. So 0.007 moles of HNO3. According to the equation, for every 1 mole of HNO3 that's used, I generate 1 mole of water. So I know then I'm going to make 0.007 moles of water. They ask for amount, so typically that's grams, so I'll just convert that to grams of water. And 1 mole of water is 1802 grams. If you left it in moles, that's fine, because they really didn't specify what amount or what unit they wanted it in. So 0.007 times 1802 gives us 0.126 grams of water. Okay. Now, they want the OH minus in excess. So that means you're going to do the rice box. We have our reaction. We know our moles initially of this and of this. We know we don't have any of this to start or any of this to start. So this is what this was, if you remember, our limiting reagent. So that's going to go down by 0.007. Now the nice thing about this reaction is everybody's a 1-to-1 ratio. So if this went down by 0.007, this went down by 0.007. And this went up by 0.007, and this went up by 0.007. So at the end of this reaction, I have no HNO3 left. I've neutralized all my acid. I have 0.00996 moles remaining of my KOH. I have 0.007, I'll keep going, of my KNO3 and 0.007 of my water. But they wanted the OH minus concentration left over. So I have the moles of OH minus. To get the concentration, I would have to divide that by the liters. And what liters? The total liters. So if we go back up here, we have 28 mils and 53 mils, which is 81 mils, which gives us 0.081 liters, right? So we take 0.00996 and divide it by 0.081, and we get 0.123 molar is your concentration of OH minus in excess. That's what remains. So it really isn't a neutral solution because we didn't add exactly enough base to react with all the acid. We had leftover base, so the solution would be basic. We'll do a couple demonstrations with this tomorrow and some more calculations. And eventually, of course, a titration lab is coming with this. Have a great night, everybody. Bye-bye.